Hi guys, it's Miss Simon. So I wanted to make this video today to help you guys out with your lesson on science. So yesterday, you guys should have done a lab that was called Race to the Bottom. And like you guys saw when I did it, you guys should have found those items and dropped them and seen which items took the longest to hit the floor and which hit the fastest. So with you guys doing that, you should have saw that the paper, the loose leaf sheet of paper, the flat paper, took the longest time to hit the floor. And we should have made the connection that was because the air friction was having more of an effect on that loose leaf sheet of paper, okay? Again, not having to do with the weight, it's having to do with the air friction. So today, we're gonna kind of continue on with our notes on gravity. Okay, so we've been talking about the other day, we also learned that with gravity, gravity pulls things straight down to the center of the earth. And there's kind of been three scientists that have really done work with gravity. We talked about Aristotle, who strictly just observed. We talked about Galileo, who actually started experimenting. And then we talked about Newton, who actually applied mathematics to everything. So today we're going to continue on with Newton, and we're going to talk about his properties of gravity that he came up with. So kind of he actually wrote down what he figured out about gravity, and we call them the properties of gravity. Just like you kind of hear about Newton's laws, okay, these are Newton's properties of gravity. So let me share my screen with you, and I'll be able to show you guys the PowerPoints, and you can add those in your notes. So make sure that if you do not have your notebook, you get your science notebook so you can add these notes down. Okay. So today we're gonna talk about those properties of gravitational force. So here are the three properties that Newton came up with. Okay, Newton was the person who again applied mathematics to gravity, but he actually wrote these properties down. Just like Newton has laws, Newton has properties of gravity and properties of gravitational force. Okay, so go ahead in your notes, properties of gravitational force. Okay, you don't need to write these down yet because we'll go through them one at a time, okay? But please put down properties of gravitational force. All right, so here are the three properties that Newton came up with. The first one he stated was it's an attractive force between objects, and each object pulls on the other one with the same force. The force increases as either object gets bigger, okay? So basically he said that gravity is attractive, okay? Just like what we talked about when we've had markers, okay? When we drop a marker, the marker is attracted to the center of the earth. So gravity itself is an attractive force, okay? And each object is pulling on the other, just like we saw with the example of the cow. The cow does have force on the earth, just like the earth has a force on the cow. Just like this marker is pulling down on the earth, just like the earth is pulling down on the marker, okay? As the objects gets bigger, okay, the force increases. Okay, so obviously the earth is having a much bigger effect on the marker than the marker on the earth because the earth is so big. Okay, but they are both attractive forces. Both of them are attracted to each other. The second thing he discovered was that every object, whether big or small, creates a gravitational field. Other objects within this field feel an attractive force. So every object, no matter what, has a gravitational field around it. Doesn't matter if it's marker, doesn't matter if it's you yourself, doesn't matter if it's anything. And everything has a gravitational force, okay? And the third one is the distance between the centers of the objects changes the strength of the force, okay? So if things are closer together, they're gonna have more of an attractive force than if they are farther apart, okay? So the distance matters on the strength of the force, okay? So now we're gonna look at these points individually. That's why I said we don't really need to write these down yet because we're gonna see them again. All right, so properties of gravitational force. All right, let's look at this first one, okay? So the principle number one is what we call attractive force. Okay, so go ahead and write that down. Write that down. Right? So gravity is an attractive force between objects, and each object pulls on the other one with the same force. The force increases as either object gets bigger, okay? So gravity kind of doesn't discriminate, okay? Everybody's gonna have gravity. Doesn't really matter if you're a small ant or a big skyscraper. Everything has gravity, okay? And it's attractive. Just as much as that skyscraper is attracted to the earth is attracted to that skyscraper, okay? So go ahead and write down gravity is an attractive force between objects and each object pulls on the other with the same force, okay? The force increases as either object gets bigger, okay? Just because an object is bigger doesn't mean it has more gravity, okay? So it's just increasing the force of the gravity. Okay, we can kind of look at the comparison between that and our other two non-contact forces that we talked about. Remember, our other two non-contact forces have been magnetism and electric forces. So with magnetism and electric forces, they can attract each other and repel, okay? So remember, with those two forces, with magnetic and electric forces, like charges and forces are going to repel each other, okay? Where unlike are going to attract. But gravity is different. Gravity only has an attractive force, okay? Gravity is never going to repel. Everything is going to be attracted to gravity. So that's important to know. Remember, magnetic and electric forces can either attract or repel, but gravitational force can only attract, okay? And if you want to underline can only attract, that's very important. Gravity cannot repel, where magnetism and electric forces can, okay? Gravity can only attract. Give you a minute to write that down before we move on. All right. Okay, this kind of goes a little bit more into that principle number one, attractive force. So unlike magnetic electric fields, a gravitational field depends on the mass of the object. To measure a gravitational force, the object must be gigantic. Each object pulls on the other one with the same force. This means that if Earth pulls on the apple is pulling on Earth. So why do you see the apple moving and not the Earth? Okay, so we can look at that. So the same thing with your marker and dropping it, okay? We see the marker moving and it's being attracted to the earth, okay? But we see the marker moving, but we don't see the earth moving. And that's kind of what it's talking about there. Just like we see the apple falling off the tree, being attracted to the earth, okay? But we don't see the earth being attracted to the apple, okay? But it is, all right? And that has to do with the mass of the objects. We know that the mass of the earth is a lot bigger than the mass of that apple, okay? So to measure a gravitational force, the object must be gigantic, okay? Each object pulls on the other one with the same force. This means that an apple, then Earth pulls on the apple and the apple is pulling on the Earth. So they're pulling on each other with the same force. We just see the apple move because it has less mass than the Earth. All right, so I'll give you a couple minutes to write that down. All right, moving on. Again, if anytime during this video you're not finished, just pause it, finish your notes, and then replay the video. Okay. So the forces are exactly the same. So again, why don't we see the Earth moving, but we see the apple, or we see the marker, but not the Earth? But Earth is so incredibly big and heavy that the force can't budge it, at least not that we can measure. However, the same force applied to a tiny apple moves it quite quickly. What would happen if everybody on Earth jumped up and down at the same time? Okay, so we can kind of look at this in perspective. So exactly like that happens, we see the apple move because the apple has such a small mass compared to the Earth. The Earth is huge, okay? And Earth's mass is huge. All right. So even though the forces are exactly the same, Earth is so big, so we don't see it move. Okay, so go ahead and write down that first point there. So even though the forces are the same, the Earth is so big and heavy that the force can't budge. Okay, that small force of that apple has really no effect on the Earth whatsoever because the Earth is so big. But again, it's still, the forces between the two are still exactly the same. All right, and the second point here says, what would happen if everybody on Earth jumped up and down at the same time? So if every single human on Earth, on the count of 3, jumped and landed at the same time, we would see the Earth move, because at that point, the force between the Earth and the people making the force are going to be great. So at that point, Earth would actually move itself. Okay. So let's kind of go through a question. There's a very small gravitational force that attracts ants to humans, okay? Is there the same gravitational force attracting humans to ants? Okay, so like we said in the beginning, everything has a gravitational force to something else. Every gravitational force is attractive, okay? So yes, humans and ants have a gravitational force that's attracting each other, okay? But there's a small attractive force between ants and humans. So they're asking, is the same gravitational force attracting humans to ants? Okay. If you chose yes, you are correct. Okay. Because like we said, the gravitational force is the same no matter the object. Okay. Everything is being attracted to everything else with the same force. The more mass, so the more weight something has, the more gravitational force there is acting on the object. True or false? So the greater mass something has, the more gravitational force is acting. You should have said true, okay? So that's the concept of why we see that apple fall, but we don't see the Earth move, okay? Because the Earth has such a great mass, that's why we don't see that gravitational force being affected by the Earth. But again, it is still there. Everything has an attractive gravitational force. All right, let's look at principle number 2. This is where Newton talks about the gravitational field, okay? So every object, whether big or small, creates a gravitational field. Other objects within the field can feel an attractive force, okay? So let's look at principle number 2 and go ahead and write down that first fact there. Okay, so any object has a gravitational force, okay? It doesn't matter if it's as big as, again, a skyscraper or as small as an ant. Both the ant and the skyscraper are gonna have an attractive gravitational field, okay? Every object has a gravitational field, okay? We don't see it, okay? We don't look at an ant and go, I can see your gravitational field, okay? You don't see all these little lines coming off of the ant, or we don't see all these little lines coming off of the Earth, but we know it's there. Every object has a gravitational field around it, okay? So let's go ahead and copy that down. Any object within the Earth's gravitational field will feel an attractive force towards Earth. So again, everything is attracted to Earth. Everything wants to be pulled down to the center of the Earth, no matter how big or no matter how small. All right. And that third principle that Newton talks about is force versus distance, okay? So gravitational force depends on distance. So go ahead and write that down first. The distance between the centers of objects changes the strength of the force, okay? Like magnetic and electric field, a gravitational field decreases as distance increases between the objects. All right, so gravitational force depends on distance. Oh, sorry guys, I know it's doing that. Gravitational force depends on distance. Okay. The distance between the centers of the object changes the strength of the force, okay? This one is similar to magnetic and electric fields, okay? Just like in magnetic and electric fields, the closer the objects were together, the greater the force. The greater the distance between the objects, the less of a force. That principle is the same for gravity as well, okay? So force matters with the amount of distance between the two. So objects that are closer together are going to have a greater gravitational attraction, where objects that are farther apart are going to have less of a gravitational attraction. So go ahead and copy those 2 points down. Okay, and this can be explained from these pictures here. It says, in which pair is the gravitational force the smallest? Okay, so in which pair is the force going to be the smallest? Well, we can look, and 3 is going to be the smallest because those two objects are the farthest apart. If I was to ask you which was going to be the greatest, you guys should choose 1 because those are the closest together. So distance matters when we're talking about the gravitational force. Okay. Newton understood that as the distance between 2 objects increased, the gravitational force decreased. Okay. So as our distance increases, our gravity decreases. Okay, so Newton understood that as 2 objects increased, the distance increased, gravity decreased. Okay. So again, we would see 3 as the least amount of gravitational attraction. All right, let's go through these questions. Which of these has the greatest force of gravity on an object on its surface? The Earth, Sun, Moon, not enough information. So which of these has the greatest force of gravity? Okay, well, we know that gravity doesn't exist anywhere else but in space, okay, as we know it. So we would say the Earth. The Earth has the greatest force of gravity. Okay, where would the force of gravity due to Earth be the strongest? So on the Earth's surface, 10 meters away, 100 meters away, or 1,000,000 meters away. So which force of gravity would be the strongest? Remember, strongest is the shortest distance. Okay, so the shortest distance would be A, on Earth's surface. Does the sun exert a gravitational force on the Earth? Okay, well, like we said, everything exerts a gravitational force. Okay, the Earth on the sun as well as the sun on the Earth. So your answer here should be yes, everything has a gravitational force. Does Earth exert a gravitational force on the sun? Well, yes, if everything has an attractive gravitational force, the Earth would exert a gravitational force on the sun as well. On the side of Earth opposite of you, things fall up away from the Earth. So this question is saying that things on the other side of the world, if people drop something on the other side of the world, it's not going to fall down, it's going to go up. Is that true or false? Okay. Hopefully you said false, because as we know, everything is attracted to the downward. Everything is being pulled downward to the center of the Earth. It doesn't matter if you're here in America or on the other side of the world, like in Australia. Everything is being pulled and attracted downward to the center of the Earth. Is there a gravitational force on Saturn due to Earth? Yes or no? You should have said yes. Again, everything has a gravitational attractive force. Everything. Just because it's in space doesn't make a difference. And 56, the gravitational force is greater on an object that is 10, 15, or 20 meters away. So which of those is going to have the greatest gravitational force? Well, if you're looking for greatest gravitational force, things that are closer together are going to have a greater gravitational force. So 10 meters away would be your answer there. Okay, so hopefully this video was helpful. So those are our 3 principles that Newton came up with, okay? So if we review them, our first principle is that gravity is an attractive force. Gravity only attracts, okay? Our second principle is the fact that everything is attracted to everything else, and every object has a gravitational field around it. It doesn't matter how big or how small, every object has a gravitational field. And our third principle is that force versus distance. So the closer together the objects are, the greater the gravitational force. Okay, the farther apart they are, the less the gravitational force. All right, so this lab here you guys will do next week on Monday. All right, so I hope that this video was helpful. So for today, all you guys are doing is you just put those notes in your notebook. And tomorrow, I'm not going to do a video, but you're going to have a Google Doc that you're going to need to answer the questions on, just like we do in class. It's like the classwork homework questions for this section, okay? And I'll have you guys be able to edit the Google Doc individually, okay? So you can just go in and I'll make a copy for each of you so you can just type your answers right on the Google Doc. So hopefully this video was helpful, and I'll see you guys soon. Bye.